an equilibrium size distribution, and we already have a bit of a range here. But of course, when you assume the wide range of size distributions that you could potentially have, the numbers, the range that you find is much larger, right? So there is much more uncertainty. So that's because we don't know if there is an equilibrium size distribution, right? So if I assume this wide range of sizes, then you get that the numbers are more uncertain, but they are still high. So the bottom line here is that, well, there is a very wide range of possible values when taking into account all these unknowns regarding the size distribution and also the uncertainty, the velocity distribution. For the velocity distribution, I think in the future what we should do is take into account also the ejection process, because I am assuming that the velocity distribution is basically given by the velocity distribution of the stars that are ejecting these bodies, but there is also these bodies are being ejected with a given velocity distributions, and I haven't folded that in. And in the future, we would like to narrow down these estimates by learning more about what is the number density of these objects, what is their size distribution, and what is their velocity distribution, right? And I wanted to mention some of the things that are being proposed here. Of course, we have STScI coming up. It's going to tell us a lot about what is the size distribution, hopefully. And microlensing surveys are going to be pretty hopeless, because with microlensing, you'll get down only to Mars size, and it's not clear that there is going to be a characteristic size that is going to connect these Mars-sized objects with, objects of the size of Oumuamua. But then Siraj and Loev suggested stellar occultations, which I think is a very interesting idea, to use stellar occultations, and they estimate that you can maybe detect one interstellar object per year, and this will help us characterize the number density. And also they suggested interstellar meteors. So they identified that there is an interstellar meteor about half a meter in size that was detected, that is coming clearly, that is clearly interstellar. And they suggest, and maybe you can tell us a bit more during after the talk, they suggest to have this network to actually study these meteors, and if you detect them pre-impact, you can actually take a spectra and see what these things are made of, which will open a new window of opportunity to learn, what is the compositions of these planetesimals that, in this case, will be coming from stars that are in the halo, so it will be very old. And the conclusions, also just for curiosity, I wanted to know, related to the interstellar meteors, I wanted to know if we could have had, if one of these meteors that we have in the lab, could it be coming from the interstellar medium, could it be one of these interstellar objects? So I compare the flux expected so I have a population of objects, I can scale that down to the sizes that are characteristic of the meteorites and the micrometeorites, and I can compare that, I can see what is the flux of this type of interstellar meteors and micrometeors, and compare that to what we observe on Earth. And what I see is that what we observe is many, many orders of magnitude higher than what we expect from the interstellar medium. So I don't think that none of our meteorites in the collected samples are coming from the interstellar medium, just based on this. And just the conclusions here, well, the British surveys indicate that planetesimal disks are common, and we think that this is evidence that the planetesimal formation is a robust process. Dynamical simulations tell us that the ejection is very efficient under a wide range of planetary architectures, so we think that the interstellar medium is filled with objects. There is the possibility that these objects could have been exchanged between planetary systems when the stars are still embedded in the cluster. And then some of these objects will be crossing the solar system and detected as extrasolar objects, extrasolar asteroids or extrasolar comets, right? And we actually detected one of those, but we have a lot of trouble accounting for it. Its visit left many questions open, and one of them was the origin and the number density, and we still don't know what is the number density of these objects. And there is the possibility that these objects can be trapped in star-forming environments and act as seeds for planet formation. But in order to address many of these things, we need to better characterize these objects, and I think we are just starting to, this is just one object. We cannot really characterize anything based on two objects, right? In particular, them being so different, right? So we are very much looking forward at what the future bring us in this regard, and that's it. Yes.
So you have the same 3 orders of magnitude discrepancy for Oumuamua and Borisov, right?
Yeah, basically.
So they're both indicative of a non-isotropic distribution, perhaps.
Yes.
But are they consistent with being from the same nearby object, or the orbit?
No, they're coming from very different orbits.
That's what I thought.
Yeah.
So you have to have 2 nearby objects. If you want.
Yeah, which will, I mean, for Oumuamua, I mean, it depends how big Borisov is, right? If it is, where is Borisov? Here. So if Borisov is small, if it were small, which is within what we have only a factor of 10 to account for, so it's not 3 orders of magnitude. But yeah, we still have a problem. But they cannot be coming from the same system, right? Yeah, and then with Oumuamua, I will talk about it at lunch. But I mean, this was just one of the open questions that it left. But we have no idea of its physical properties. It's a very strange object. So, and Borisov was very boring because it's just comet, right? Which I find it interesting, the fact that it's very similar to the solar system comets, right? Which is also interesting in its own shape, right? Yeah.
So just continue on this point. Couldn't you take the systems around us and make a more specific model for our location and the nearby systems and try to see?
Because the Oort clouds are touching each other.
But in terms of
so it covers the sky. The nearest star system.
So what do you mean when you say non-isotropic? Then it is isotropic.
The separation between stars is roughly the size of the
Yeah.
Oort cloud. So think about it as billiard balls touching each other, and they're covering a huge fraction of the nearby stars are covering a huge fraction of the sky.
So when Amaya says that it's not consistent with isotropic population, what's the alternative? Because you're saying now this is the only possibility because already the Oort clouds are touching themselves, so you're already in kind of isotropic situation. You cannot have a non-isotropic population, right? At least from this point of view. Anyways, so that's just one point there to think about. But my other question was about the seeds. So you said that this might be a way to overcome this. What was it, kilometer barrier? Or
no, meter
barrier.
size
Meter barrier. But I mean, you'd have to form them somewhere.
Right, so this only helps out, and later on when the galaxy.
It will only help some systems to help.
It cannot help the first generation.
To form these
yes,
sizes.
but I guess the idea is that you wouldn't need fine-tuned conditions for all the disks. That in some cases, maybe you
but
could
it
have
can't
this.
be a general. It can't be a general explanation.
No, right, yeah, and I don't even know if those numbers are enough. Right, I mean that's something. I mean they look pretty high, but I don't know how many do you need, right? Where is? Oh, I don't know where it was. Yeah, so here. So I don't know. I mean it's like 10 to the 15, 10 to the 12, but I mean it seems like a high number. You don't need that many planets to form, right? But I don't know how many are enough.
So going through molecular clouds will slow down many of these interstellar objects that don't get captured. Right? So you're cooling the gas of interstellar objects effectively, reducing their typical losses.
You don't.
Thus making them easier to capture.
Actually, they don't change much. If you look at.
But you have some that are captured and some that are not captured, but must be an intermediate range.
Right, the ones that are captured are because they are already coming at the velocity that is smaller than the escape velocity. But the gas,
so there's no serious cooling.
There is the gas doesn't really.
Slow down.
They don't slow down.
We calculated this, and you'll need to go through all the galaxies.
Yeah.
To slow down.
You can. I calculate here. I didn't show you this because, but this is like the final velocity after it crosses the whole environment. And basically, if you throw them at 30 kilometers per second, the final velocity is still 30 kilometers per second. And there is this plot here. It basically calculates what is the final velocity, the ratio of the final velocity with respect to the incoming velocity. For the typical cloud, this is for a pre-stellar core kernel, so we are at 10 to the 6. You will need to be basically several orders of magnitude higher in order for it to have an effect. Which, if you look at what is the ratio of R, basically the column density, yeah, it makes sense because you will need to have it closer to 1, which is the whole argument of that you really need to have enough column density in order to stop the momentum, right? So you are a couple of magnitudes, a couple of orders of magnitude off. So the gas drag doesn't do anything. So yeah.
Basically, the column density of the ISM is about 10 solar masses per parsec. And yeah, but this is the mean ISM. It takes into account some regions with cloud, some regions with less density. So the mean is like about 10, give or take a factor of 2.
Eric has a question.
Yeah, it seems to bring up this inconvenient conclusion that the Oumuamua might not be an interstellar object in New Zealand. So I do the best I can, I make all these calculations, and then I can't account for it. And then it's, well, maybe it's not an interstellar object. For example, the Voyager probe is now on an interstellar orbit, and it would be very hard to account for that by a statistical argument, because the community designed it to be ejected from the solar system.
So you think it could have a solar system?
Maybe Oumuamua got boosted by planet X or something.
It would have to be, I don't know.
I mean, I don't want to argue about that suggestion,
The
but
chance for that is very small. Outside the solar system, the velocity at infinity was 20-something kilometers per second. So
It was 26 kilometers per second, right?
Right.
relative to the sun.
right, but okay, I shouldn't have brought up my suggestion because then you're going to argue against that. But the point was, I mean, it doesn't help the